Chapter 5. The ADM formalism. In this chapter, we analyze spacetimes that have metric that can be written in the form. See equation 5-1. This is often referred to as the lapse and shift formalism due to ADM, or simply the ADM formalism. Doing the Riemann tensor calculation for a particular ADM metric or local ADM metric is often very difficult, such that the solution approach is not only important to get a solution, but to get a solution with useful groupings of variables for the analysis that follows. For this reason, 4 separate approaches are described. 1. The Cartan approach. 2. The extremal path method. 3. The 3+1 split method with geodesic path method. 4. The change of basis method. The methods can be used in combination, especially method 4. Some examples are shown for each of the approaches. 5.1 The ADM lapse and shift formalism. Consider see equation 5-2.
For a general action we have, see equation 5-3, for which we must calculate 4r. Calculation of 4r is done in 3 ways. 1. Via exterior differential forms. W to the alpha goes to W sub beta to the alpha goes to R sub beta to the alpha goes to R sub alpha delta gamma to the alpha. Section 5.2. 2. Via extremal path method. Section 5.3. Via 3+1 split. 4r equals 3r plus kk, 3r equals 3 gamma plus 3 divergence. Since the gamma s and the 3r are based on a coordinate frame, it is easiest to calculate them using the geodesic path method, section 5.4.
In addition to the above 3 ways to evaluate 4r, it is often advantageous to perform a change of basis first, and these methods are described in sections 5.5 to 5.7. Sometimes it is easier to calculate the Landau form of the action, which uses, see chapter 2, see equation 5-4, where gamma sub beta gamma to the alpha is the tensor obtained by incorporating the added structure of a reference basis. The reference basis is chosen so that the connections fall off sufficiently at the boundaries so as to yield no boundary contributions to the action. See equation 5-5.
The choice of basis is indicated by the choice of boundary conditions. For asymptotically flat sections at spatial infinity, the Minkowski reference basis is appropriate. This reference basis is chosen not just at the boundary, as in approaches that retain second-order terms in the integrand of the action. Rather, the reference basis is chosen throughout the spacetime. Calculation of the gamma s is done by first calculating the gamma s for a coordinate frame, necessary to avoid structure constant terms in the calculation, via the extremal path method if not in coordinate frame, then see section 5.6. The gamma s are then evaluated in the basis of the Minkowski reference fluid, and interpreted as a tensor gamma. 5.2 Evaluation of 4 are using exterior differential forms, Cartan method, so, starting with the metric written in lapse and shift form due to ADM, see the equation shown. Where
see equation 5-6. Choose for basis 1 forms as follows. See the equations. Thus, see the group of equations shown.
See the equations. Thus R sub v to the mu equals dw sub v to the mu plus w sub alpha to the mu wedge w sub v to the alpha. See the group of equations shown.
See the equations. Thus see the group of equations shown. And using see the next equation, we get
see the equations. Now calculating the R, see the group of equations shown.
See the equations. And see the group of equations shown.
See the equations. R sub v to the mu equals R sub v times the absolute value of alpha beta to the mu w to the alpha wedge w to the beta wedge R equals the mu th v th power of g of R sub mu v equals the alpha th beta th power of g of the gamma th delta th power of g of R sub alpha gamma beta delta. Thus, see the equation shown. Equals 2 times R sub 101 to the 0 plus 2 R sub 202 to the 0 plus 2 times 2 R sub 212 to the first plus R sub 323 squared, the latter step due to spherical symmetry, and see the group of equations shown.
See the equations. Now putting together in the Lagrangian density and simplifying, see the group of equations shown. Thus see the equations.
See the group of equations shown. Thus see the equations.
See the group of equations shown. Thus see the next equation. Take script L raised to the 1 as the volume contribution to the action, then see equation 5-7. See equation 5-8. Inverting. See equation 5-9. See equation 5-10. Substituting back into the Lagrangian, and separating in the usual Hamiltonian form given by the Legendre transformation. See equation 5-11. See equation 5-12.
See equation 5-13. H has regained a second-order term through elimination of n' by integration by parts. This was required to separate the n as a Lagrange multiplier. Surface terms arising from n' are not a problem if 4r is evaluated in terms of the gamma prime s, with non-tensorial divergences dropped. This eliminates second-order terms at the outset, as well as n' terms. When taken for change of basis to that for which the derivatives in the gamma prime s can be taken as covariant, a tensorial interpretation results. This approach may not need surface term corrections as in the usual ADM.